We are finally ready to talk about integrals in terms of multivariable functions. What we want to start out with is the simplest of these types of integrals. So we're going to talk specifically about iterated integrals and then just areas with rectangular region. So what I want to do is I still want to show you where everything comes from the same way we did in Calc 1, how these formulas come about, because remember we always take this complex problem and we break it down into smaller, more manageable pieces, and we use some kind of approximations that we know how to find area or volume for in this case. So what we're going to do is see where this double integral is basically going to come from, because when we start talking about more complicated ones, we're going to have to talk about different coordinate systems and be able to switch things around. So it is important to kind of see where these pieces come from to make that stuff in the future a little bit easier. So we're going to start and we're going to assume we have a function z. So suppose that z is a function of x and y, and this is continuous and positive. Over a rectangular region R. So this region R is all the xy coordinates such that x is trapped between A and B, and then y is trapped between C and D. Okay. What I want to do, and it doesn't necessarily have to be positive, it's just kind of helping us out for this specific example. But remember, you can have something like negative area, same kind of idea, you can have negative volume. So in our case, because it's positive, that means it's lying in the top octants. So I want to find the volume of the solid underneath that function over this rectangular region. That is our whole goal. So 2 dimensions, you were finding the area under a curve above that x-axis. Now in 3 dimensions, we've got that function sitting in the top octants. We're finding the volume of that over some region in the xy plane. So if you think about the easiest thing to find volume of, that's going to be some kind of rectangular box, because you just do length times width times height of the box. So let's start with that. Let's try to approximate the volume using rectangular boxes. So I'm going to do my best to draw a really nice picture for this. So here is our 3D coordinate system. I have some rectangular region here, so it's got nice bounds, because if we make these complicated, then it is much more difficult. And so this is our region R that we're trying to find the volume on top of. So this is R. Okay. So the x values that this is changing between are A and B. So here's the start of the x, the end of the x, and then y is changing between the values C and D. Okay. And so I have this function that's just up top here doing whatever. What I want is specifically above this box. So I'm going to say maybe it has values like this, and then this back one I'll make a dotted line, but maybe it keeps going up like that. So this is the back of the box. Okay. So maybe it curves down a little bit. And I'm trying to find the volume of this thing. So up top here are the z values. Okay. So I want to basically slice this up just into partitions like we did before of equal sizes. I'm going to slice the x-axis into however many equal portions, and then I'm going to do exactly the same thing in the y-axis. And so basically you're making a grid down here over that region R, and you're going to find the volume on each sub-interval of this grid. Okay, so we're going to have some typical box that will approximate the volume. Okay, so maybe on this particular slice, the graph would go up to here. And again, I'm going to use a rectangle because finding the volume of a rectangle is much, much, much easier. Let's see if this one will go straight. There we go. So we are just approximating the volume with a box. Okay. So this is our typical box that we're using. Okay. So I'm going to give you the thorough process again for this, but in practice, you're not going to evaluate a limit. But what we can do is we can partition the interval a to b into m subintervals of equal length. And specifically, that length, remember, is delta x. The way you find the length is you take the length of the interval, which is b minus a, and you divide it by the number of subintervals. And then I'm going to do exactly the same thing with my y component. However, it doesn't need to be the same number of subintervals. So instead, we're going to partition the interval from c to d into n subintervals of equal length, and that length is delta y. So we take the length of this interval and divide it by the number of subintervals. Okay. So it's exactly the same thing as in Calculus 1, where you took that x-axis, you had the interval from a to b, you divided it into equal pieces, and then on each of these subintervals, you would pick a point, and you would plug that into your function to get the height of your rectangle. So we can do the same thing here on this grid. I can pick any point I want to find the height of my box. Because when I go to find the area of this base, it is length times width. Well, the length is delta x, the width is delta y. So all I need is my height to get my approximating volume. Okay? All right. So I'll show you in a better picture what that looks like. But really, we can pick any point inside the base of the box. To approximate the height. What we ended up deciding to do in Calc 1 is we typically use the right endpoint. So here I'm basically doing the same thing. It's going to be the top corner because it would be the rightmost x value and then the bigger of the y values. But we'll do examples where again we can use anything. But for now, let's use the corner of the partition. Okay. So I'll show you what that corner looks like after I draw my grid. So we're going to just jump to 2D and look at what's going on in the XY plane. Our X is varying from A to B. The Y is varying from C to D. And this creates my rectangular region R. Is a bigger tool for that. That would take way too long. So in my X direction, I'm breaking this into M subintervals. Okay. So let's use a dotted tool, make this a little nicer. So I don't know how many subintervals it is. We'll just do a couple. But again, they're all going to be equal length. Okay. So this particular interval would be xi minus 1, and then it ends at xi. And then we're going to do exactly the same thing. Let's use green for that. In the y direction. But again, these can be different amounts of subintervals. So maybe this one has like 5. Okay. So this can be something completely different. So n subintervals. Okay. And so maybe I'll specifically look at, let's see, we'll do this box. Okay. So this value, once you break this down, break this down, this value here would be yj, and this would be yj minus 1 right before that. So if I'm picking the rightmost endpoint for the x, it would be one of these 2 points that I would utilize. But if I'm doing the same thing for the y, I'm going to pick the bigger value. So we're essentially using this upper right corner to find the height of the box. So the actual coordinates of that corner would be xi and yj. Okay. So I can use a rectangle or a rectangular box. The base is a rectangle, so it's length times width. The height, I'm using the z value, and I'm just plugging in this value into the function to get the z value or height. So essentially, we've got this approximating rectangle. So this is that base. This is the corner that I'm using to approximate. The length on one side is delta x. The length on the other side is delta y. And then we're using a rectangular box. If I can make these stay straight, close enough. Okay. All right. And then our height is going to be the function evaluated at that corner piece. So our volume is just the product of the three. So we would take the height times it by the length and the width. Okay. Then what I'd have to basically do is on every single one of these grids, I would have to use that right corner to go ahead and find the height. And then you're always going to multiply by delta x and delta y because that's the area of that base. So essentially what I need to do is I kind of have like a pattern going on. When I go to find each of these points, the x is increasing, but the y is staying constant. Then when I move on to the next row to find all of those endpoints, again, the x is increasing, but that y stays constant for it. And so I'm going to run through every possible combination for my x values and my y values. So you're going to see it's going to create a very large sum. Okay? So what we can do is we can approximate the volume of the solid by the following. So we've got it approximately. So starting with this first row, my y is staying fixed. It's my first y value, so y1. And what I need to do, this would be x1, x2, x3, and then I keep going up to xm because there's m subintervals. And my y is staying fixed for all of these. So to find the heights, you run through every x value, and then you would times it by delta x and delta y. You get the next x value, but y is still the first one we're using. And then I keep going until I hit my last endpoint, which would be xm, because there's m subintervals. And my y is still on that first row. Okay. Now I move on to the second row. And so again, now this is x1, y2. Then this next one would be x2, y2. And you keep going until you hit xm, y2. And so adding up the volume of each of these boxes, we really get the same thing, except the y has changed now. And then you keep going in that row until you reach that last subinterval. Okay. So you get a nice pattern going on. The x's change this way, but they're constant as I go downward. Okay. So really what's happening is your y value is increasing in the downward direction. Your x value is increasing in this direction because we're basically going through a snake pattern to hit the corner of every single one of these rows. Okay. So I have to keep doing this until I hit my very last row. So I'm just going to do dot, dot, dots. And then we run through all the same x possibilities with the very last y value, which is yn. So before we just had a sum from 1 to n of our xi's, but here now I have to go through every single possible combination. Okay? So what that means is my volume is actually equal to a double sum. We have our xi and yj. These two things are changing, but delta x and delta y stay put. My I is going to start at 1 and end at n because that's what x is changing through every single time. And then my y starts at 1 and goes to n. So the j subscript varies between 1 and n. Okay? So you had a single Riemann sum back in Calculus 1, but now to find a volume, we have a double Riemann sum. And what we would do to find the true volume is you would split those intervals up as small as you possibly can, and you're basically letting the number of subintervals for both of the values x and y approach infinity. So taking more and more rectangles leads to the volume of the solid. So our volume is exactly equal to the limit as both these number of rectangles approach infinity of this double Riemann sum. And if you remember what that turns into, it becomes just a bunch of integrals. Okay? So the sums and the limits would switch over to that full integral. Delta x turns to dx, delta y turns to dy. And then for our bounds, it's just going to be the values x is changing between and the values y is changing between. So we end up with two integrals over our function, and then dx, dy. The order is important because x is the first here. That means the integral closest to it is going to be its bounds. So here x is changing from a to b. Okay. This is going to be why putting your dx and dy is super important and why we're such a stickler on making sure you have proper notation, because this dx dy tells you the region you're integrating over and the order in which you need to do it. If you're not putting these, it is going to make this chapter almost impossible, because the stuff that we're going to get to is going to be much more complicated, and these play a role in what happens. The order of integration is going to matter, okay? So absolutely, you need to get into a habit of that. Because now y is the outermost that will correspond to this integral. And so our y changes between c and d. Okay? So this is our formal definition for an integral. Okay? What we often do, instead of having to write dx dy, because you might have to come up with the order of integration, and especially if we have a different region, we usually just call it r, and then we have dA to represent dx dy. So to show you that notation, if we let dA equal dx dy, and delta A to represent delta x, delta y, the change in the area in the xy plane, then the double integral of f over the rectangular region R is defined by the following. We have a double integral. The region I'm integrating over is R. We have our function inside, and then we're integrating with respect to x and y. And again, that order depends on the problem. This is defined really in terms of Riemann sums. It's the limit as m and n go to infinity of a double sum where we have the function evaluated at the right endpoints of those intervals, and then delta x, delta y, which is the change in area. The x starts at 1 and goes to m, and the y starts at 1 and goes to n. Of course, provided that this limit exists. So let's try an example where we're going to approximate the areas, but then we're actually going to find the integral itself. So hopefully this isn't too bad of a process for rectangular regions. When you're finding a double integral, you just start with the innermost variable. So you integrate whatever function you have with respect to x in this case. And so you treat your y just like a constant, and you differentiate or integrate x as you normally would. So reversing your power rule, finding the antiderivative of whatever trig function you have. Then you'll evaluate it at these bounds, and then your x should totally disappear. Then what you're going to be left with inside is completely an integral with respect to y, which you then find. Right? But again, let's try to approximate the area or the volume, now that we're in 3D, of a particular function on a rectangular region. So we're going to estimate the integral I. So I is going to equal the double integral over the region R. Our function is 1 minus xy squared dA, where R is a rectangular region given by 0, 4 cross negative 1, 2. Specifically using a Riemann sum or double Riemann sum with m equaling 2 and n equaling 3. So again, everything always goes alphabetically. This is the x values, and I'm splitting that into 2 subintervals. And then these are the y values. I'm splitting that into 3 subintervals. So I'm going to need all of my endpoints. I'm going to draw out my grid because that's going to make life a lot easier. So my x is from 0 to 4. My y is negative 1 to positive 2. So I need a little bit of that 4th quadrant. So we'll go out 1, 2, 3, 4. And we're going to go up 1, 2, and down 1. So my region R, we'll go ahead and highlight. Y changes between negative 1 and 2, and x is changing between 0 and 4. So this is the region I'm finding the volume under. So I need to see how big are my subintervals. You can use your graph. You've got to split the x direction into 2 equal pieces. So each box is going to have a width of 2. But again, to find that delta x, you take the length of the interval, which is 4 minus 0, divided by the number of subintervals. So 4 over 2 gives us that each subinterval should be width 2. So my grid in the x direction gets split right here. Okay. Then my delta y, I want this to be in 3 subintervals, and this is length 3. Just to show you, you would take 2, subtract -1, and then you would divide it by 3. That gives you 3 over 3, which gives us 1. Okay. And let's go ahead and make these colors match just so it is consistent. All right. So splitting this into our grid, we're going to have y equaling 0, y equaling 1, and y equaling 2. Okay. So from this, I'm going to go ahead and approximate the volume in 2 different ways. The first way I'm going to do that is by using upper left corners. So a little different than what we started with. And I'm going to go ahead and cheat and copy my grid down here first. If I want the upper left corners, I basically have 6 boxes, 1, 2, 3, 4, 5, 6. On each of these 6 boxes, I want to use the upper left corner. So that would be this one, right here, here, and then these last 2. These are the points that I'm going to use to approximate the height. So specifically, this first point here is 0, 0. We're going to plug that into the function to find the height on box or region 1. For region 2, we're going to use the point 2, 0 to find the height. Moving on to our third box, this point here would be 1, 0 or 0, 1. So that's the y value. On region 4, this corner right here would be the point 2, 1. So we'll use that to approximate the height. On box 5, this point here is 0, 2. And then on region 6, this box here would be 2, 2. Okay. So again, you can see the x value goes up by delta x each time, and then the y value goes up by delta y each time. And we're plugging this into our function, which if I go way back up here, it's 1 minus xy squared. So I'm going to trust you could definitely plug these values in to get the z value corresponding to it. But what this does is it tells me my integral is roughly about equal. I take my first point and then I times it by delta x and delta y. So I would plug that into the function to get the height, and then delta x and delta y are the area of the base. Moving on to the next point, I would plug in 2, 0, and I times that by delta x, delta y. Okay. And then just to keep this in a nice grid, I add my next point, which is 0, 1 times delta x, delta y, and then 2, 1, delta x, delta y, and then going on to that top row, 0, 2, and then 2, 2. Okay. Realistically, again, you can just take out the delta x and delta y, and you would go ahead and add all of these function values together, which is the beauty of using rectangular regions. Okay, so this tells us then our integral is about equal to, if I plug all of those values in, times delta x, delta y. So if you plug 0, 0 into here, well, that's just 1 minus 0. So the first value is 1. if I plug 2, 0 in, that's also nice because the product is 0. So it'll be 1 minus 0. That y value or z value is 1. If you plug in 0, 1, same thing because x is 0. We're going to get the z value as 1. When I plug in 2, 1, this would end up being 1 minus 2. So that height is negative 1. When I plug in 0, 2, same thing. This will give me positive 1. And then the last one, if I plug in 2, 2, that would be 2 times 4. So 1 minus 8. This gives me minus 7. So our integral is about equal to, if I add all of that up, it ends up being negative 4. Delta x is 2, and delta y is 1. So as a rough estimate, the integral is equal to negative 8. So all that means is that most of this function is sitting below the xy plane in the bottom 4 octants. That's all negative volume is associated with. So let's try this a second way. Instead, let's approximate this using lower right corners. You could also pick the midpoint of each of these. So another possibility is you're picking the point dead center of the box. That's more annoying to calculate though. So I'm going to go ahead and duplicate this again to help me find those z values a little bit easier. So let's figure out all of the right points we're going to use to approximate the height. Now on each of these regions, I want to use the lower right corner. So that would be these 6 points to approximate my rectangle's heights. So starting with the bottom row, this point here would be 2, negative 1. Moving on, this point would be 4, negative 1. This will be 2, 0. This one is 4, 0. This one is going to be 2, 1. And then you can see our last one is the point 4, 1. And I'm going to plug all of these into the function to get the z value for our approximating height. Okay. So in this case, our interval will be about equal to, I take all of these function values. So I plug in 2, negative 1, 4, negative 1, 2, 0, 4, 0, 2, 1, and 4, 1. And then I times that by delta x and delta y. So this tells us this integral is, again, I'm going to trust you could plug all of these values in. This first one should give you negative 1, then negative 3. Positive 1, negative 1, and negative 3. So those are our 6 values. Delta x is 2, and delta y is 1. Okay. So multiplying all these out, this will end up equaling negative 12. So with one approximation, we got the integral is about equal to negative 8. The second approximation, the integral is equal to negative 12. So we don't know exactly the true integral yet, what that area is, but at least it gives us an idea. If I took more subintervals, I would get a better idea as to what's going on. Problem is, that would take a lot of time to compute by hand. So instead from here, let's actually find this integral. So we've got the double integral over the region R. The function on the inside is 1 minus xy squared. And then we're integrating with respect to x and y. So I need two integrals. I'm going to do the order dx dy. My x is this first integral. That's changing between 0 and 4. And then my y is the outer one. That's changing between -1 and 2. So I'm ignoring this outermost integral. You really don't need this step. And what I'm doing is I'm calculating this first integral that deals with x. So when I go to calculate this, I'm integrating with respect to x, just like when you were finding partial derivatives. Here, when I'm integrating with respect to x, y is treated like a constant. So for this, again, I'm going to put these markers. If I were to integrate this with respect to x, this first one, the antiderivative, is x. The antiderivative of x would be x squared over 2. So you bump that power up by 1, divide by the new power. And that y just stays attached. And then I'm going to use these bounds from 0 to 4. And again, these are x values. So I still evaluate it the same way, but I'm replacing x by these constants. So if I plug in the upper bound, that will be 4 minus 1/2 times 4 squared. The y squared stays attached. And then we subtract, plugging in 0 for x. And you can see now our x is completely gone, and I'm just left with something dealing with y. And that's what I want, because now I'm integrating with respect to y. Before I do that, I'm definitely going to clean this up though. So this front piece, really, the second one is just completely gone. This is all 0. So the front becomes 4. 4 squared is 16 times 1/2. This becomes 4 minus 8y squared. And then we integrate with respect to y. So finding that antiderivative now is much nicer. Antiderivative of 4 is 4y. Antiderivative of y squared is y to the third, and then divided by 3. So we really get 8/3. And then evaluated from -1 to 2. And this, I trust you can plug this in. This ends up equaling -12. So one of our approximations did actually give us the true volume of that solid, right? So only in this section do I not really have to worry about the order. When I have a rectangular region, whatever way I set this up as dx dy or dy dx isn't going to matter. You can pick the variable that's easier to integrate with respect to first. Completely up to you. However, this is pretty much the only section that's going to happen in. In our future sections, the order makes a significant difference. The reason we can do that is something called Fubini's theorem. So when I have a rectangular region, it is the nicest possibility as to what can go on. So Fubini's theorem states that if we have a function f of x and y, we're going to let this be continuous on a rectangular region. And again, that is a key component. This only works on rectangular regions. So our region R is all x and y, such that our x changes between the constants a and b, and the y changes between some constants c and d. Then, if this is the case, if you want to find the double integral over this region, the order does not matter. So you can set this up as dx dy, or you can set this up, need a little bit of room there because I got to go add the bounds, as dy dx. In this first case, the inside bounds would be the x bounds, the outer would be the y, and then in this second case, you really have the freedom to flip, okay? But this only works for rectangular regions. You are not going to be able to flip-flop bounds. You'll see why in a future section, but basically instead of having constants on this innermost integral, you're going to have variables. And you can't just flip-flop and have variables on the outside. Because for us, this double integral is representing the volume of a solid. You shouldn't end up with a function in return. And if this outermost thing has variables, the last thing you're doing is evaluating with variables. And that doesn't result in a single number. You should always get a nice number for these. Okay. So to show you that for a rectangular region, we absolutely can do this. I'm going to go ahead and I'm going to do an integral two ways. I'm just going to switch the order. And again, it's completely up to you which one you pick. In some instances in the future, one way is going to be more preferable than the other. But at least while we're starting out, the order isn't too significant. But you want to do the least amount of work for yourself. So we're going to evaluate the integral from 0 to 2, 0 to 4, y cubed e to the 2x. And this one is dy dx. And then we're going to go ahead and we're going to flip this. So 0 to 4, 0 to 2, y cubed e to the 2x, dx dy. Okay. So I'm going to start with my first one. I like to call these I because, again, we're going to have to be writing a lot of equal signs, and it's tedious to have to keep bringing this integral down. So we just call it I. So when I'm going about this, again, I'm starting with this inside expression, integrating with respect to y. So this is just a constant. I'm just going to integrate y cubed. So the 0 to 2 is untouched. When I integrate y cubed, that's y to the 4th divided by 4. The x stays untouched, and then we're going to evaluate this from 0 to 4. And again, these are y bounds. So I like to put that in here just to remind myself which variable I'm replacing by that constant. So going through and plugging in 4, you have 1/4 times 4 to the 4th times e to the 2x minus 1/4 times 0 to the 4th, which that's always nice because this second piece just becomes 0. So really what this simplifies to, 4 to the 4th divided by 4 is 4 to the 3rd. 4 to the 3rd is 64. So this is the integral from 0 to 2 of 64e to the 2x. And then integrated with respect to x. So if you need to use a u sub, you can, but really using u subs for constants at this point is going to give yourself a worse headache than anything. So instead, if you think about e to the 2x, its antiderivative is e to the 2x. But because I have a 2 that's in here, when I would go to actually take the derivative of this, the 2 would pop out. So I have to do the opposite. I need to divide by 2. And then we go ahead and evaluate this from 0 to 2. So that really gives us a 34 out front. And then we'll plug in 2 for x. So this is 34e to the 4th. Or sorry, not 34, 32 e to the 4th minus 32e to the 0. And then just to clean this up so we can see that these things end up being equal to each other, e to the 0 is 1. Okay. Now I'm going to do exactly the same thing, but I'm going to reverse that order, and it better end up giving me exactly the same result. So reversing the order, we're still calculating the same integral. We're just switching those bounds. So we're going to do dx, then dy. X is changing between 0 and 2. Y is changing between 0 and 4. So you're going to see this way is actually quite annoying in comparison to the first one. That didn't take us too long. But here we're going to have a little bit more work to do. So I'm going to keep my 0 to 4. And what I'm going to do in here is integrate this expression with respect to x. So the y cubed just stays attached. That's just a constant. Antiderivative of e to the 2x would be e to the 2x. But then I have to take care of that constant. I get a 1/2 out front. And then we're going to need to plug in these bounds of 0 to 2. And this time I'm replacing x by this value. Then I'll go ahead and integrate with respect to y. So plugging in the upper bound, this gives us 1/2 y cubed e to the 4th minus 1/2 y cubed e to the 0. Okay. And then I'm going to go ahead and factor out stuff that's common to both of these because I'm going to need to take the antiderivative of this, and I sure don't want to take the antiderivative of each of these separately. So really, both of these have a 1/2 in common, and they also have a y cubed. I accidentally copied down the wrong one there. Okay, because that y cubed does not change. From the first piece, I'm then left with e to the 4th. From the second piece, I'm left with e to the 0, and e to the 0 is just 1. But when I'm going to evaluate this integral, 1/2 is a constant. This is also a constant, so both of these can pop outside the integral. So this becomes 1/2 e to the 4th minus 1. And then we're taking the integral from 0 to 4 of y cubed. And that alone is hopefully not too bad. That's just reversing our power rule. So it gives us y to the 4th over 4. And then we're going to evaluate this from 0 to 4. Okay. So if I combine these two constants, 1/2 times 1/4 is going to be 1/8. Or also you can go ahead and just evaluate this I'll do it that way just to show you. This would be 1/4 times 4 to the 4th minus 1/4 times 0 to the 4th, which thankfully just turns to 0. So we really get 1/2 e to the 4th minus 1. And then same thing ends up happening here. 4 to the 4th divided by 4 is 4 to the 3rd, and 4 to the 3rd is 64. So combining those like constants, 1/2 times 64 is 32, and that's times e to the 4th minus 1. So this is exactly the same thing. It just takes more work to get there. Okay? So again, make sure when you're doing homework, you're writing these down thoroughly. You're adding dx's, you're adding dy's. You need to be able to write these things crystal clear so that everyone can follow when they're looking back through your work, because it is going to make anything after this point extremely difficult to do if you're not writing your dx's and dy's and having a clear thought process through your integral.